Okay, great. Guys, for doing that. This is our last official quiz. I mean, as I sent a message and mentioned on Monday, for those who are here, we're gonna have another one, but that's, if you do poorly, it won't affect your grade, but if you do really well, then it can help you out. So, I just want to be able to get that last material on there. And if I do, I'll have to put everything on a quiz at some point, so it'll be great. Okay, so today, I guess before we hop into small one, our main topic, I want to mention a little bit because when I picked up the problems, it was a little bit ago, so I forgot what some of them, especially for 4.6 were. And so let me take an example from 4.6 just to kind of understand how to go about it. So this is in section 4.6 again, and this is going to be problem number 5. Okay, so on this problem, what's happening, right, is it gives us 4 different kind of boundaries. And the first boundary is y equals x. So that's just kind of a normal line about 45 degrees. It gives us x equals -1. So I'll put that here. So this is x equals -1. This is y equals x. We have x equals 1. And finally, we get the, maybe I'll it's a boundary. And then we have the x-axis. Or this is the same thing as y equals 0. Okay, so this is the picture, right? So in the problem, you're just given the bounds, right? But this is one of those where it may seem you may want to draw a picture, right? I would always encourage you to draw a picture if you could, especially if they give these numbers, because that could throw things off. If you're just given a couple of curves, like I gave you on the quiz, it should be pretty straightforward for the most part. You're just sitting where they hit each other if you don't have any numbers. But if they give you more, you might see what's going on, because you might be working with more than you expect. So what areas are we finding here in this case? If we're finding what's bounded between all these curves and lines.
Right triangle, top right triangle along the x-axis.
Bottom right triangle. Bottom left triangle. Gotcha. And then upper right. Top right. So these two, right? Okay. Now, in the examples we did in class, right? We were trying to figure out which one's on top and which one's on bottom in order to be able to do our area, right? But in this section, is there one that's always on top and one that's always on bottom? No, they switch, right? Because in this section, the line is clearly the curve that's above the x-axis. But in this section, it's the x-axis that's above, right? And because of that, since it switches, I'm going to need to split this into 2 different integrals. Okay, where I do the process that we learned in class a couple of times. Okay, so I'm going to call this triangle, we'll call this triangle number 1, and I'll call this triangle number 2. Okay, so for triangle number 1, okay, we're going to be doing an integral. What are the bounds of that integral going to be? So for number 1, right? So not 0, 2, right? So okay, so we're bounded on the right side of x equals 1, right? That's what this line is. So my x doesn't go past that, right? If you say x equals 2, x equals 3, that's over here, right? So we can't go past here. So 1 is definitely our right boundary, right? Now I'm just talking about this triangle, right? I'm not talking about this triangle. So what is the left side of this triangle? It's 0. So I'm going from 0 to 1. Okay, and you can find that too if you want to say, okay, well that's where y equals x hits the x-axis, which would be when x equals 0, right? Just as a way to confirm that. Okay, but that would be that triangle, right? Now in that area, right, 0 to 1, what curve is on top? Y equals x. Good. So x is on top. So I put x first. Which one's on bottom?
Y equals 0.
Y equals 0, the x-axis, right? So then that's gonna be second. So maybe just to put in the forward, like a, how we've structured it. Now, in this case, it doesn't matter much, x minus 0 is just x, right? So you can just evaluate it as x, but this is the area of that first triangle. Okay? But notice we're still using the f of x minus g of x here, we just had to separate it into different pieces, right? For the second triangle, what are my bounds gonna be? -1 to 0. Okay, so again, farthest we go is left is -1, and I stop here at 0. Okay. Now which curve is on top? 0 is on top. Yep. What's on bottom? X. So now my integral is the integral from -1 to 0 of 0 minus x dx. Okay, and that's that triangle. Okay, so then once I do both of these, calculate amount, which they should both be 1/2. After you do that work, that's just 4.3, 4.4, 4.5. So I add them together at the end, right? Because now remember again, the whole subtracting part where we did f of x minus g of x, that was here. We did that already, right? But now we're just saying I found this area and I found this area. If I want to get the total area, then I sum the two, right? And so I take 1 plus 2 to get the total area, right? Which what's 1/2 plus 1/2? 1. So 1's my answer. Okay. If you just assume that 1 was always on top and 1 was always on bottom, and you did like x minus 0, and then did from -1 to 1, you would get 0. But if we look at the picture, right, that's not going to be correct, right? When we were talking about negative areas and kind of keeping a standard form, that was true, but now we're not interested in that anymore. We just want to say, I have two things, I want to know the area between them, right? And so that's why we need to split it up. Okay, questions on that? Yeah. Yeah. So I'll just talk about it for 1, right? So 1, we go from 0 to 1 of x minus 0, which is x, on z, right? So this is just a definite integral, right? What is the integral from, how do I find the antiderivative of x? Right, so to evaluate this, I take the antiderivative of x, which is going to be x squared over 2, and then I plug in 0 and 1, right? So I get 1 squared over 2 minus 0 squared over 2. What's 1 squared over 2 minus 0 squared over 2? 1. 2 is similar, except you have a little bit of sign stuff to figure out, but otherwise it's the same. Basically the same idea. Okay, again, the game here is that every time we're working with these, we need to be getting the positive area of some sort, right? Because if I say I'm going to find the area between two curves, I would hope that it's a positive area. I shouldn't have anything negative, or I shouldn't be getting 0, right? So if you get a negative or 0, you might check and make sure everything worked out right. Usually a negative case is just, flip the sign of it, make it positive, but sometimes it may be more than that. So pictures always help, not always necessary, but if there's a whole bunch of bounds, might consider drawing a picture. Okay. Good. Okay, so that is 4.6. Any last questions here before I move on to our last couple of sections? Okay. Let's erase this. Okay, so now we're going to move on to section 5.2. Okay, notice we're skipping 5.1. You feel free if you want to read them on your own. I'm not required to teach it as far as I am aware of what I was told. But it's basically talking about using integrals to find kind of averages and find means. Typically if you're finding the mean of something, you add up all your numbers together and divide it by the total number of terms, right? But that's just if you have different, like a set of numbers you're doing. But when it comes to functions, we have to get a little more intricate, a little more to find all the values. So, okay, but in 5.2, we start talking in 5.3, we start talking about finding volumes. Okay, so it may seem like a big jump first to go from, because we were just talking about doing areas and finding areas. Now we're going to be able to find volumes, which you guys won't ever have to take like count through or anything, so you won't have to worry about kind of working with more complex 3D shapes to find the volumes of those. But we do actually have neat ways to find shapes if they're just rotating, right? So imagine if I took, if I have a function that looks like this, right, on a section, right, and I want to find what's called the volume of like its rotation, right? What that means is that I take, let's say like my center line is here, so I'm finding, just looking at this section, then I can get the volume of, I have a nice way to get the volume of the shape that looks like shape that looks like this, right? So I just took the curve and I flipped it around, right? And all I needed to know was not necessarily what's happening on these sides, but I just need to study kind of what's happening on the basic curve. Okay. So in order to kind of build this, to start arguing how we can find this volume, right? We always start with something easy, which is a rectangle. Okay. We build everything off of rectangles. That's how our integrals are made, right? So I'm just going to take this shape and I'm going to look at, I'm just going to take a little rectangular section, okay? Which I can make that infinitely small, just like how we've done with integrals. But I'm going to take a rectangle, okay? And then I'm going to take this rectangle and I'm going to rotate it around best of my ability. But we just kind of get one ring, essentially, in that shape. So it's going to look something, maybe to draw it differently, it'll look something like, we're kind of getting the disc that looks something like this. Okay, and with this being a disc, right, there's no crazy curve shape on it. It's just like this side is flat. So I can easily, like, first of all, well, actually, if I were to draw this differently, kind of look at this upwards, this is just a cylinder, right? I'm just getting a cylinder shape. Something like that, right? How do I find the area of how do I find the volume of a cylinder? Yeah, we take pi r squared, right? Which, so that's the radius of this circle. And so pi r squared is just the area of that top circle. And then I multiply it by whatever the height is, right? That's h. And that's similar for our kind of coin shape that we have here with our disc, right? So that is for that small rectangle and that small disc that I cut out is that volume, right? Of just that particular section, right? And so the idea is that if I take that volume and add up all the volumes together, right, of each individual cylinder, then I can get the total volume, right? So how we're going to work with this, right, is, remember, so this is, we were kind of looking at it sideways to understand we're working with the cylinder, right? But in our case, let's figure out what exactly our radius and height is in this case, right? So again, we have a center line, right, that we're cutting through, and this is our function, right? And then we've made a rectangle that has some small width, we'll call dx in this case, right? So what is the radius essentially of the circle that we cut out?
The height.
It's kind of not necessarily that height, but it's the distance from here upwards to the top, right? Which is f, which is the function, right? So my radius in this case is essentially whatever my function is, right? And now again, going off this picture, so we have a radius, we need a height, right? So again, turning this on its side, what would my height need to be in this case? It's your delta X or it's your dx, right? So again, I'll say H in this case is dx. Okay, so taking that together, right, along with the pi term, and then again adding everything together, which would normally be in a sum, but then we turn it into an integral, we get that the volume of this surface is going to be, and let's say that we start at A and we end at B, right? This is going to be the integral from A to B of pi times f of x squared, right? Because that's our radius. Theta. Like that. Okay, so that thing on the inside is the volume of each individual kind of cylinder we cut out, right? And so then we add up all the cylinders together using the integral, and that's our volume. Okay, and this, there's another way we find to do volume, which is in 5.3, but this method in particular is called this way. Okay, so something to keep in mind. Okay, so when you're asked to do this method, this is exactly what you should be thinking of. Okay, so if I'm wanting to find the volume of basically the surface of rotation, this object of rotation, made by the function, I just plug it into this formula. Okay, just takes all those little cylinders and add it. Okay. Good. Any questions so far on this? So maybe so. So let me know. I'm trying to the system. Okay. Let's see. Okay. No, so they go ahead and we'll start off with an example first. Okay, example 1. Okay, so let's say that I have, right? So I want to convince you that this works, right? So we're going to start with the shape that we're familiar with, right? Which is that, let's say that I have this arc here, right? Which, so this left point is some negative positive number r, I'll call it, and this right point is is the positive one, right? And this curve itself is the square root of r squared minus x squared. Okay, so I'm giving this to you. I'm giving that curve to you, right? When I rotate this, right, I'm going to rotate about the x-axis again. So we're starting with the x-axis. We're rotating around. What's going to happen? So let me try to move this bottom part so you can see it. I get a shape that looks like this. What is this shape? What is this? It's a sphere, right? We know how to get the volume of a sphere, right? Anybody remember what the volume of a sphere is? Yeah, so in general, yeah, so to get the volume of a sphere, if I know the radius of that sphere, it should be 4/3 pi r cubed, right? So if we do everything right, we should get this, right? We should get this answer out. So let's try it. So this is our function, right? So again, sometimes it's pretty helpful to draw where this rectangle is at, so we know where we're working, right? So kind of what we need to get. So here's our row. I'll just draw a rectangle here, right? And so I'm taking each little cylinder and rotating around the x-axis. Okay. So in each case, right? So I have the integral from. Okay, what do we think? What's the bounds of the integral going to be in this case? Negative r to r. We're going from negative r to r. Yeah, a lot of people speaking there. That's great. I'm hearing all the voices. Okay, negative r to r. Okay, and okay, so the next part is so we're gonna start plugging into this, right? So we have the pi, right, which kind of gives us a rotation. What's my radius in this case? That's like the thickness of the cylinder, right? It's sort of the height part. What's the up and down? Yeah, what is it? Well, right, but when I talk about the radius, I'm talking about the part that goes here, right? Kind of the, right, we've tilted it on its side, so this is the radius I'm looking for, right? So I'm talking about the up and down in this case. So it's gonna be f of x, right? It's gonna be our function, which in this case is r squared minus x squared, right? So we take square root of r squared minus x squared, okay, pi r squared, and then put the dx on it, right? So that they give us our thickness of each cylinder, give us the height in a way. Okay, so we just need to work this out. Okay, what happens when I do r squared minus x squared square root squared? Yeah,
I would just, isn't it supposed to be cubed?
where?
Like the function that's in there, isn't it supposed to be cubed? That's the problem.
No, so we're not using this, right? We're wanting to show that this equals this. But we're not getting there yet, right?
Alright.
So we're using the function we've been given, which is in terms of squares, right? Okay, so we have the square root of r squared minus x squared squared. What happens to the square root and square?
Just go away.
Yeah, they cancel each other out, right? So we're gonna get pi, which again, pi is a constant, right? So oftentimes it's easiest, we can just go ahead and take that pi and move it outside, yeah. And we'll just worry about it at the end, right? So we have negative r to r of r squared minus x squared. 8. Okay, do I know how to find the integral of that? Hope so. Okay. So this is gonna be pi. Okay, what is the integral of r squared dx?
R cubed over 3.
It would be if it was dr. It's dx, right? R is just a constant. Again, R is just a number.
I would go outside. Yeah.
Right, so let's recall, right? Let's recall. So if I'm just integrating a constant times dx.
Oh, R squared x.
Good, it's r squared x. Yeah. So we get r squared x. And then what's the integral of x squared dx? 1/3 x to the third power. Good. And then we're taking this from negative r to r. Okay, so now we just plug things in. Okay, so this is going to be equal to pi, and so we're going to have, when we plug in r, I get r squared times r, which is r cubed. Okay, minus 1/3 r cubed, right? Again, just putting r in there, and then minus, we're gonna have put a negative r in here, so that gives us negative r cubed, and then negative 1/3 times negative r cubed. What's that gonna be? What is it? Right, so what happens when I take negative r to the third power? Right, obviously, so I can take that 3 to each part, right? If I take negative 1 and I raise it to the third power, is it negative 1 or is it positive 1?
Negative.
It's negative, it still remains negative, right? If you take a negative number to an odd power, it's still negative. And then we just have r to the third power. So the negative just kind of sits on the outside now. Okay, so we get negative r cubed, and then you have this times negative 1/3, which gives us plus 1/3. Like that. Okay. Then we can add things together. So we get pi. So we have, let's see, r cubed minus 1/3 r cubed plus r cubed minus 1/3 r cubed. Okay. So we get pi times r cubed plus r cubed is 2r cubed. And then we have minus 1/3, which is minus 2/3. Oops, that's r cubed. Oops. Okay. What is 2 minus 2/3? It is supposed to be 4/3, right? So 2 I can rewrite as 6/3. right? Using an common denominator. And then that's gonna give us, and I'll bring that 4/3 out to the front. Pi r. So like it looks. Okay, so that is our volume, right? So the volume of this shape that we just made is 4/3 pi r cubed, right? Now, I won't say that there's not any examples in the book that are gonna just have like some random variable that you plug in. It's actually good practice to be able to do that just because sometimes I may not want to just get one integral, but I might want to get a class of them. And so that's why I'm just having a random number like r, right, to plug in helps me out a lot. But hopefully I've convinced you that this works and it makes sense. Okay. Any questions here? We'll do an example that doesn't have just a random r in it. So comments, concerns, questions, anything? Okay. Let's over here. Okay. Let's see what example we've got stored next here. So okay, so actually, before they get to the next example, we have something else to talk about, right? So the reason that I wanted to do 4.6 before, like save it just until we do this next section, is because now I'm considering the possibility that I have one function. Yeah, we have another function. And I'm gonna want to get the surface that's made up from going in between the two, right? So I have one, basically there's one surface that's being made like this, and then there's another one that's being made that looks like this, right? Okay, but I don't want the stuff in the middle. I only want what's formed on the outside of it, right? So imagine like taking maybe an easier picture. Right, so I don't want to just get one fixed cylinder. I want to have a cylinder and then cut a hole through it. That's basically what's happening, right? Does that make sense, right? So imagine G is kind of like the inner one, and this is the outer one. Okay, so I only want the outside. Okay, so on a thinner scale, kind of like what we did with the last one, right? This may just look like the book usually calls it a washer, right? You know, like when you're working with tools, you have a washer. And so that's what we're aiming for. And so the way to do this, right, is similar to how we find the area, like the volume between two cylinders, right? So if I have one bigger cylinder and one smaller cylinder, and I want to take out the smaller cylinder, right? So let's say that the bigger cylinder is has a volume pi big R cubed H, and this inside cylinder has volume pi little r squared H. Now, if I want to find the volume between the two, what do I do with those two? You just subtract them, right? I have a bigger volume, a smaller volume, take away the smaller volume, just subtract it, right? So the volume of this whole shape, right? So again, that's the outer cylinder, is going to be pi times big R squared minus little r squared times H. Okay, again, they both have pi and H in it, so I just factored it out. Okay, so that gives us that volume. So how this applies here, in this case, this is basically just a small extension of the disk method, which is called the washer method. Okay, if I'm going from A to B, right, and I want to find the volume between these two, I have pi, and then I'm going to take f of x squared, which is the top one, minus g of x squared, which is the bottom one. That's the end. Okay, so instead of just squaring one function, I square two. right? So I'm gonna have f of x squared and g of x squared, so I subtract the two. Okay, and so again, we'll do sample this one. This is again called here. They're essentially, the disk and washer are essentially the same thing though, right? Like if the problem just asks for disk and you have two functions to worry about, you're probably gonna end up doing washer, but they're one and the same, right? Because essentially you're just subtracting two disks. So that's all it is. Okay. So we're gonna move on to example number 2 at this point to put this into practical use. So we want to, so we have two terms, we have the line y equals x plus 3. We have the parabola y equals x squared plus 1. Okay, so let's take a second and sketch a picture. So tell me about this line, right? What is what's the slope of this line? 1. What's the y-intercept of this line? 3. Okay, so I move up 3, and then I have a slope of 1, 1 over 1, 1 over 1. So it looks like this. Okay, and then x squared plus 1, right? Graph a normal parabola, and then just move it up 1 step, right? That's all it is. So if my normal parabola is here, I just take everything and I bring it up 1 step. So I actually get this step. Okay, so this is my shape. And now I want to figure out. So now I'm considering, okay, so I want the spacing between them. So again, here's another rectangle. Maybe I'll put a rectangle here. So right here, the volume we want. And I'm wanting to find the volume by rotating this around the x-axis. Okay, so I'm taking this, rotating around, right? So I get some an interesting sort of shape. It's a bit hard to draw. Maybe I'll at least try to get the general picture here. Kind of like a weird wave of sorts. But we don't exactly have to know what it looks like to know what we're rotating, right? So again, I'm rotating all of this section here, right? So first thing, I need to get my bounds, right? How do I get the bounds in this case?
To each other.
Set them equal to each other, not set them equal to 0, right? Because if we set them equal to 0, that would tell us where they hit here, but actually that wouldn't help us, right? We want to see where they equal each other, right? We want to see where they clash each other, because that's where the section stops. So I'm going to take x plus 3. I'm going to set this equal to x squared plus 1. Okay. How should we solve this? What is it? Subtract, oh, this one? Or, oh, here, you're subtracting this to this side, or, okay. Yeah, so we can do that. I might actually suggest for now, let's leave the, since the x squared is very positive, let's just go ahead and bring everything to that side to make it easier. We could also put this over on that side, but I'll subtract the x and 3. So we're gonna get x squared minus x minus 2, and that's going to be equal to 0. Does this factor? Yes. What does it factor into?
Minus x plus 1.
X minus 2, x plus 1 equals 0. Good. So what are my 2 x's?
2 and negative 1.
X is 2, x is negative 1. So these are my boundaries. Okay. There's no other boundary to worry about. I'm just worried about those 2 numbers, right? So I'm going to go from negative 1 to 2. And now we just use our formula, right? So I take pi, and then I take f of x. What's f of x in this case? Which one's on top? The x plus 3, right? It's the one that's more kind of outside, right? So we take x plus 3 squared minus, okay, and then we're going to take g of x, which in this case is x squared plus 1. Squared. Yeah. So and then that's all set, right? So this gives us everything we need. So we're gonna have to do a little bit of work. So we're gonna have, I'll bring the pi out. Let's x plus 3 squared.
I have one question.
What is it? Yeah.
Since it goes from -1 to 2, do we split that up or do we keep it? Like
So-
-1 to 0.
So from -1 to 2, does it change which one's on top and which one's on bottom? No, it does not, right? And then because of that, we don't need to write 2, right? On the problem we did at the beginning, you had, it was x was on top and then the x-axis was on bottom, but then it flipped in the other case. That doesn't happen here, so we don't have to worry about that, right? So it's gonna be, so this is gonna end up being x squared, right? And then we take, so remember if I take a plus b squared, this is a squared plus 2ab plus b. If you need to FOIL out, feel free, it's fine. This is just a little shorter way to get it here. But we're gonna get x squared, right? A squared plus 2 times 3 times x plus 6x plus 3 squared plus 9 minus, okay, and then similarly x squared plus 1 is going to give us x to the 4th plus 2 times x squared times 1 plus 2x squared and then plus 1 squared. Okay. So we get this point. Okay, again, that's just that's spoiling. You can always feel free to write on the side and work it out if you need to. It helps out. But we definitely need to know how to do that. We're just kind of taking a shorter formula of sorts. So we get pi from -1 to 2. Okay. Now we have, let's see. So I have x squared minus 2x squared, which is what? Minus x squared. Yep. We have 6x. Nothing, there is no 6x term there. We have 9 minus 1. What's 9 minus 1? 8. Good. We have, and then we just have negative x to the 4th. Okay. So from here, you just kind of work it out. Do I need to go through this? I know this is a bit longer of a problem with the different terms, but it's you just multiply by pi at the end, and that's going to be it. So do I need to go through this, or would I be able to go ahead and do another example of like how to set it up? Here.
Okay.
Yeah, because it's minus x to the 4th, right?
Oh,
Mhm. Yep, so we have x squared minus 2x squared, negative x squared, 6x minus nothing, 6x, 9 minus 1 gives us 8, and then negative x to the 4th is over there. Okay, so I'm just combining terms together. Yes,
So we're trying to find the area in between the line and the parabola as it rotates.
so not really. We're not finding an area, right? I'm rotating the shape, right? And I'm finding what the volume of that shape is that it's rotated, right? And so the volume is going to be given by this. I'm not taking an area necessarily. I mean, no, because the area between them would just be x plus 3 minus x squared plus 1, right? But notice we're doing squared, right? So I can't just do the area and then multiply it by 2 pi or something. I have to a little bit more goes into it, right? So just think about it as I have a couple different shapes, right? A couple different cylinders, right? Then I'm finding the volume of, and then I'm subtracting those 2 volumes from each other. Just like here, right? I have a bigger cylinder, a smaller cylinder, subtract the 2, right? of course, the integral's fine there, just to add things together, but at each step, that's what's happening, right? We have to do a little bit of 4-point checkerboard work to get there.
Thanks.
Any more questions on this? I didn't hear anybody opposed, so I think I'll go ahead and just do another example, avoid all of the kind of number work there. Okay, so let's see. Okay. So now the next example here is I'm gonna find the volume of a solid. So let me go ahead and I'll write all the words out here. Find volume of solid by rotating region bounded by x equals the square root of y equals 4, and the y-axis okay. So in this case, we're not given a function of x, right? We're given a function of 1. But again, let that not be something that scares us, right? Let's just, if we need to, we can always draw a picture to see how it's set up, and we'll probably do something similar to what we did in the x-ray, right? So we draw this picture out. We're gonna have, so x is the square root of y. If you did solve this for y, you would get y equals x squared, right? Square both sides. And so that's gonna look, at least it's just gonna be the right side in this case, but it's gonna look like x squared up on this side, right? Because if x is only the square root of y, I can't get negative numbers, right? I can't get -1 out of square root of y. Okay, so we're just left with here. Y equals 4. What is y equals 4? Is that a horizontal or vertical one? Horizontal. Okay. So we'll say that's here. Y equals 4. And then the y-axis. Okay, which is here. Okay, and now we're rotating it about the y-axis as well. Okay, so I'm taking my shape and I'm rotating it around. Get this nice shape. It's called a gravel. Pretty fun. So okay. And let's keep in mind, so on the examples we were doing, we were kind of thinking about our rectangle that kind of gave us each cylinder was up and down, right? It was kind of sitting on the x-axis. So now we're going to want to sit it on the y-axis, right? So it's horizontal, right? But we're still taking it and making a cylinder out of it. We're just looking at it in a direction. Sorry, that's bad. Maybe bad drawing. I think you understand what I'm going for. So let's go ahead and find that volume, right? So I'm going to take integral, right? Again, because we're adding up. What are my bounds going to be in this case? What is it? So a 0 is correct. I think I heard someone say -2 to 2, right? We're keeping things in terms of y here, right? If you try, there's a way you can solve this to put it in terms of x, but that requires 5.3, and we haven't learned 5.3 yet, so we can't use that. Okay, so if I'm going, here's the way to remember it. If I, well, actually, I'm trying to think. So if I'm going about the x-axis, then I need to have a y equals x equation, right? If I'm going about the y-axis, then I need an x equals y equation, right? So, because otherwise it won't work for disk. It will work for shell, which we'll get to, but again, we're just sticking with this for now, right? So now my bounds are gonna be in the y direction. I'm keeping things in terms of y. So we're going from 0 to, what's my upper bound?
4.
4. We're going to 4, right? Because we're doing everything in between here, right? And that stops when y is 4, right? We're not talking about, again, you don't want to put 4 inside the x, because we're not talking about x bounds. These bounds are in y. Okay. Now, so looking at that rectangle right that I put on there, what is my radius in this case? Is it always 2? What is it? It's x equals the square root of y, right? Because it's not always 2, right? If your radius was always 2, we would just have a cylinder, right? Because you'd have a constant radius, right? But as I go from bottom to top, my radius is changing size, right? Like this rectangle gets bigger as you go up, right? So it needs to change. Of course, at the top it's 2, but it's not going to be 2 all the way through. So yes, our radius in this case, we have pi, as always, is going to be the square root of y squared. And what do I put on the end?
dy.
dy. What is the square root of y squared? Y. I just want to know what it is. Why'd you have to say y? Why dy? So what's the integral of y dy?
Y
Or the
squared,
integral? Was it?
y squared over 2.
Just plug in from there. So pi is just hanging out. We have 4 squared over 2 minus 0 squared over 2. So that's just going to give us 16 over 2, which is 8 times pi. Okay. Questions, comments, concerns? There. Okay. Again, it's the same. You might have to what you might have to do is just kind of when you do these little y ones, you might twist your head a little bit just to think about it a little differently. But you're doing the same thing, right? What would be the radius in your x direction is the same thing as what your radius would be in thinking about the y, right? You have to be a little bit careful here. But otherwise, it's the same process. Okay. Let's see. Okay. I only have a few minutes left, so I may. Let's see. I can either do one more example of disk, or I can go ahead and preview shell. I can go ahead and do one more example of this one, which would be in the y direction, with 2 curves, or if you're fine with that, just with the x example, and just switch it around a little bit, I can go ahead and give you an idea what shells looks like. Okay. Okay, great. Shell. Yes, that sounds great. Okay, good. So let's talk about shell now. Okay. The reason why I'm emphasizing those rectangles so much is because this becomes very important. Okay. What happens is that every time you do a problem like this, you want to kind of have a reference rectangle right? So when I was talking about the x direction, my rectangle was horizontal, right, or vertical. It was a vertical rectangle, but in this case, it was a horizontal rectangle for the wall. Okay. The reason I say that is, again, I'm going to take a random function again. Okay. And this is f of x. Okay. Maybe I'll just go here. So instead of going about the x-axis now, so this is a function of x, right? So I'm working with a rectangle facing this direction. But now instead of rotating about the x-axis, I'm rotating about the y-axis. When I'm stubborn, so I don't want to change my function, right? Because in order to go about the y-axis, we'd have to change it in terms of y, right? Because that's how this method works, right? Essentially, again, so we can see it, your rectangle, so the rectangle in this case has to be perpendicular to wherever the axis is, right? So since it was horizontal in this case, and this was vertical, we were good. Here, I'm taking a vertical rectangle in my x direction and rotating it about a vertical line. So I need another method, okay? Because now this shape, and I won't draw the whole thing, but I'll at least draw what this rectangle will give us. It's gonna look something like this, something actually like that cylinder we saw there, right? But instead of having to just actually cut it out, right? It's already kind of pre-cut in this case, right? Which is nice, okay? Now, this one's a little bit, like I can't, in this case, I can't really represent it well. I don't really always want to do a subtraction of two rectangles. So instead, to find the volume of this thing, I'm going to take it and I'm gonna stretch it out a little bit, right? So I have this ring, so I'll cut it here and just pull it apart, right? So I'm gonna get a shape that looks something like this. Okay, so I literally just took that ring and I pulled it apart, right? But it should have the same volume because if I put it together, it still works, right? So it has a specific radius attached, right? Which is r, right? So what is the circumference? If the radius is r to the outside, what is the circumference to the outside? To pi r. So that is the length of this section. Okay, again, this is a little approximate, but since we're working with such a small thickness, it doesn't matter. Okay. So now we have a height as well, right? Which in this case, that height, again, well, in a similar way, that height is going to be my function. Whatever that function height is, right? So that's this side. And then finally on this little edge, that's going to be my thickness in this case. So that's my dx. Okay. So you can see if I took this and I wrapped it, especially very small, it's going to be what the volume needs to be, right? So shell method says that I go from A to B, okay? And now I'm going to take all of these three things and multiply together because that gives me my volume. So I'm going to take 2 pi r times h times dx. Okay, where h, so h is the function, dx is just dx. Okay, now the more interesting part here is going to be the radius. Okay, because now we don't just have one variable we're working, the radius we need to fill in. We have a radius and a height to fill in. That height is still is the function in this case, which is good. The radius in this case is your distance, is whatever the distance is from wherever you're rotating around, right? So we'll get into this a bit more next time. But in this case, right, we're flipping around the y-axis, right? So what is, if I just take any random distance from the y-axis to where my curve is, what is that distance going to be? Any guesses? What is it?
Delta R.
Not delta r, not quite. It's going to be x, because that's how far. So basically, I'm saying this point is some x distance away from the y-axis, right? And so we use x as my r, right? Now we're going to see cases where we're not rotating about the y-axis particularly, and so we might have to adjust that radius a little bit, but it's pretty intuitive. Okay, so I'll leave it with that. Back to the next problem. Again, look at example 4 for the discussion. That helps out a lot. Yeah. First. times. It is. The Mac is open on Mondays through Thursdays. So. Now it's not as busy during those times, but it is open, so.
Thanks for watching. See ya.